about circles. This is by far my favorite topic. I love when we get to circles because this is when things start coming together. Like I felt like we got a little bit to see, we have to see a little bit how triangles help in quadrilaterals, but like everything that we've studied really feeds into circles. So that's the beautiful thing and the ugly thing about circles. Okay, so if you really struggled with one small topic, maybe it'll impact you, maybe it won't, but we see parallel lines in circles, we see triangles, we see quadrilaterals, so all those things are gonna start coming in. Okay, that's kind of what I think is so cool, how they all start working together, and you never really make the connection of how important triangles are for circles because they're just so differently shaped, right? So I like making all those connections. So last night you did, or yesterday in class, you did that circle term review, right? Any questions on the circle terms? So let's talk the vocabulary part. Are you okay on vocabulary now? My guess is if you got something wrong, you figured it out, right? As far as what it really was. Okay, what about the bottom part where you're working with arc measure and angle measure? Any questions there? Okay, so yesterday you basically dealt with central angles, right? Whether you remember that's what it's called or not, those are central angles and their arc measures. That's what we're going to focus on for a little while, for the next, I don't know, 3 days or so. After that, we start focusing on something called inscribed angles, and we'll spend, like I said, a whole day just on dealing with that. Everything we're going to do right now is central angle focus. So what we're going to do today, I have 1, 2, 3, 4, 5 properties we're going to define and talk about, and then we're going to practice using. Okay, so I'm going to dump a lot of information at you, and then we're going to practice using. All right, so the first one says if two chords in a circle are congruent, then they determine two central angles that are congruent. So this word here is congruent. So specifically for our picture, what this means is if chord AB is congruent to chord CD, then there we go. Angle 1 is congruent to angle 2. So if my chords are congruent, then those central angles are going to be congruent. In this chapter, we're going to need to bring back the segment markings because we're also going to have arc marks. Okay, and sometimes we have to distinguish between the two. So you're going to want to use them again, and I'll be using them as well. Especially if we're writing out proofs or something like that, like where they're intermingling. You have to write those little symbols. Okay, so we're going to write the formal proof for this in a minute, but let's kind of talk through why this is. Okay, so my if is the given part. So we're going to start with the fact that A, B, and C, D are congruent. One of the nice things about circles is we have basically one measurement to start with, a radius. But we know all radii in a circle are congruent. So all of those radii there have the same measure because there's the radius in the same circle. Well, notice what we just created. We created two congruent triangles, right? So those two triangles are congruent by side, side, side. And something that you're going to notice that happens a lot is we create isosceles triangles. Okay, we'll come back to that in a minute. But we created two congruent triangles. So by side, 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 we know they're congruent. And then by CP, CP, C, we can say that angle 1 and 2 are congruent. Okay, so we're using congruent triangles to prove properties of circles. All right, so let's write out our proof. So here we go. Given circle K with AB congruent to CD. Get it? Circle K? All right. All right, circle K with chord AB congruent to chord CD. That's going to be good. I'm going to go ahead and mark my figure. got rid of up to go upstairs. All right, so now we can talk about those radii. One thing that people like to do with radii is they list them all together in a row. So KA is congruent to KB, which is congruent to KC, which is congruent to KB. So they list all the radii together, one big long string, because it allows you then to mix and match however you want without having to make a bunch of individual statements. Now, you can separate them if you want. If you want to do AK and KB are congruent, and then KC and KD are congruent, that's fine too. But a lot of times with circle proofs, you'll see this big string. Okay? The reason we can say that is because all radii in a circle are congruent. Okay? All radii in a circle are congruent. I'm going to go ahead and mark those. Okay, do we have all of our parts? It feels a little awkward because I don't really have three congruency statements, right? I kind of have one and then the huge one, right? But all the parts are there. We have K, KB, and we have KC and KB. So we have our three parts. It's a good combination. So I can say that triangle AKB is congruent to triangle. Here's another nice thing about circles. Because I've created an isosceles triangle, I can either call it CKD or I can do DKC. Either way, we have some flexibility there. And again, that's because of side, side, side. And then the last step, we know now that angle 1 has to be congruent to angle 2 because of CPCTC. Not so bad, right? It's not that bad. All right. So the rest of these, we're going to kind of talk through the reasons of why they work, but we're not going to write out formal proofs. We're going to do some of them later. Okay? So the next property says, if two chords in a circle are congruent, then their arcs are congruent. Okay, so you're missing blank there is congruent. So specifically for us, that means if chord AB is congruent to chord CD, then arc AB is going to be congruent to arc CD. All right, so let's think about this one. We just got done proving that if AB and CD are congruent, that angle 1 is going to be congruent to angle 2, right? We just established that. Now, yesterday you did an assignment that if you knew the angle measure, you knew the arc measure, right? Okay, so think about this. If we have two congruent angles, the angles define the arc measure. So the angles are congruent, then by substitution, those arcs are going to have to be congruent as well. So like if this is 50, because of congruent angles, this is going to be 50. The arc is going to be 50, this arc is going to be 50. Make sense? All right, next one. The perpendicular from the center of a circle to the chord is the bisector of a chord. So the perpendicular from the center of the circle is the bisector of the chord. So we're saying if we have a segment coming from the center, it's perpendicular to a chord. What's going to happen is that segment is going to bisect those chord angles. Okay, so I'm going to make the connection back here for you. Imagine you would, if I were to draw in some radii like this. So what if I were to draw on those radii and I made that triangle? We know that the triangle is going to be isosceles, right? Okay, think back to when we studied isosceles triangles. It was the Nemo notes. I said that if you have an isosceles triangle, that the altitude, the angle bisector, the median, and the perpendicular bisector were all the same pieces, right? So look what we have here. We have an altitude, we have a perpendicular. So that perpendicular is also the bisector, right? This is the median, this would be the angle bisector, right? So those isosceles triangles, all those properties come into play a lot. Why does isosceles triangle? Because all radii of a circle are congruent. So when I drew in my radii, because they're radiuses, then they have to be congruent. That's what makes my isosceles. Does that make sense? We make isosceles triangles a lot of circles. All right, we have two more. Next one says, two congruent chords in a circle are equidistant from the center of the circle. So equidistant is the blank. So for us specifically, this means if chord AB is congruent to chord CD, then KM is going to be congruent to KN. This one is a pretty long proof, but I think it's this one's easy to see almost if you can visualize it. The longest chord in the circle is the diameter, right? So the closer this chord gets to that center, the longer it's going to become, right? And then as soon as it gets to the center, it is the largest. The closer to the edge, it's going to get shorter and shorter and shorter. So if these two are the exact same length, then it would make sense that those would have to be the same distance apart. If this was longer, it'd be closer to the center. If this one was shorter, it'd be further from the center. Does that kind of make logic sense? Okay. All right. Here's the last one. Prepare yourself, because this is my favorite one. All right, so the perpendicular bisector of a chord passes through the center of the circle. So if we have a chord and another segment that is perpendicular and it's bisecting that chord, then that piece has to go through the center of the circle, whether it's a radius, a diameter, or a whole piece of a weird segment in there, okay? This is my favorite conjecture of all time. I said this is my favorite of all times. Anyone ask me something? I'm so glad you asked. Thank you. Okay, so once upon a time, I bought my very first house. Okay, so my house was built in between 1880 and 1890. Okay, that's as far back as they could travel. Has anybody lived in an old house like built like 1800, early 1900? Okay, so you're gonna back me up on this story. When you live in an old house like that, you'll go in one day to change a light bulb, and the light fixture falls out, and the next thing you know, you're rewiring the whole room. Have you guys had that experience? You lived in an old house? Like, things just fall to pieces. Like, you think it should be so simple. You want to change a light switch, or you want to change a light. I mean, literally, I had changed a light bulb, a light fixture fell out of the ceiling, rewired the whole one. It's just bad, okay? Things just deteriorate over time. They don't make things the way they used to. Well, like now, like those components are typically better made, like wires and stuff, compared to back then. All right, so in my house, I had 2 bathrooms. Okay, and in those old homes, when you had bathrooms, if they put them in at the same time, they typically stacked them on top of each other. because then they can share some of the drain pipes. So like when you flush your toilet or drain the tub or use a sink, it goes into a big pipe that's called a soil pipe, and it travels down your wall into usually your basement, crawl space area, and then out through the ground to the sewer line for the city. Well, when they built the house then, especially back then, they wanted one big soil pipe to go out of your house. Okay. So they made them out of cast iron. Okay, they were big, big, heavy pipes. And again, they wanted to share that cast iron for both bathrooms. Well, what happens when you mix cast iron and water? It's going to rust, and it's going to deteriorate. So one day, I was getting something out of the basement, and the basement was not nice. Like, it was dug out, dirt floor. Like, I had flagstone for my foundation, like where they just literally stack rocks. It's an old house. I'm in the basement getting something out. My sister is upstairs. She flushes the toilet or drains the tub. I think she flushed the toilet, and all of a sudden I hear in my basement. It's never a good sound as a homeowner. So I go and I'm looking around. The soil pipe has corroded and collapsed on itself. Okay, which means I have no bathroom to pass. I have no way to flush the toilet, drain the tub, sink, nothing. So sadly that day I moved back in with my parents while I was getting my bathroom. Okay, so this was probably like my 5th year of teaching. So I don't have much savings at this point, you know. So it's rough. To remodel a bathroom is a lot of money. And so like you can, like thousands and thousands, like upwards of like $10,000. It's expensive to hire people because they're specialty trades. Yeah, so we decided to do it ourselves. We're going to remodel the bathroom ourselves. The problem is that now I have 2 bathrooms to remodel because it ruined both bathrooms. Okay, so we had to gut the bathrooms to the point of I'm standing on my 2nd floor bathroom on the studs that are on the floor, like the floor braces, looking down and I can see the basement floor. Okay, so I mean, like it was completely dead. So we put new wires in, new pipes in, and all that. So we have the toilet pipe. So it comes up through the wall still, and then it bends in the floor, and then it curls up to meet your toilet. Okay. So your toilet, the bottom shape is kind of like an oval, right? Something like this. Okay. It might be a little bit different. But the weight of the toilet is all held on this rim. Typically, that rim is maybe a 1/2 inch thick. Okay, and then after that, it kind of goes up and bubbles up inside. So really, all the pressure from the toilet sits right here. The soil pipe that comes from your toilet comes up, and it's fairly big compared to the base of that toilet. Okay, so you have to cut a hole in your floor for that pipe to come up, but you have to be careful so that that hole isn't ending up underneath the edge of your toilet because it creates a weak spot. Okay, so you got to make sure that that hole is right where you want it. So the other problem is you lay down subflooring, which is just like a wood plywood sheet, okay, a flat plywood sheet. You lay it down, but you got to cut a hole for that pipe to come through. Okay, well, you're covering it up, so it's hard to see. So we had to figure that out first. So we got some lipstick, put it on the pipe, laid down the board, picked up the board. Now we knew where to cut. Okay. So next question is, how do we cut out this circle? So when you're a kid, you know, you have a circle on the paper, you like fold it in half a little bit and snip it and just make a strand, right? But I don't want to cut through the board because I would weaken where the toilet's sitting, right? I would weaken that board. I don't want to mess with the integrity of it. So they make what are called hole saws. Okay, so a hole saw kind of looks like a bowl, but it has the base of it and the sides are perpendicular. Okay, and it has little teeth right here. You put it on your drill. Okay, and there's a drill bit that comes up through like this, and it sticks out. So you literally attach it to your drill, and you pretend you're drilling a hole, but it takes out a big chunk like this. Okay. So the problem is, I can't match up the hole saw to the hole in the floor because that drill bit sticks out too far. So that drill bit has to go in the exact center of this circle. Makes it a sobriety. My dad, very particular man, very detail oriented. like things are going to be right. He's going to study things ahead of time. Like when he went to buy a car, it took him months. He walked into the dealership and said, "This is the VIN number of the car that I want." Okay, okay, so he's like, "Well, how are we going to do this?" Because they can't goof it up. Like, he doesn't want to get the hole off. That would mess up with the toilet and all that. It's all kidding. Like he was pacing at my house, back and forth. Not sure how to do this. Can't measure from the wall distance and all that because first of all, we didn't have walls up yet. And then when you have studs in your old house, they're not like the 2x4s you go buy at Lowe's right now. They're like carved out. They're like wavy, like literally wavy, because they've been like literally carved, like chisels and stuff. Okay. So I said, "Dad, I've got this. I'm a geometry teacher. I can find the center of this circle." He's like, "No, you can't." I'm like, "Yeah, I can. Like, this is what I do. Like, this is my job." So this is the center of my circle. I literally went, this is a true story. Like, none of this is made up or exaggerated. I literally went and got my compass and my ruler, okay, and I did a construction. So I drew a chord. And we learned how to find the perpendicular bisector of a chord, right? So I opened my compass more than halfway, did this, found that perpendicular bisector. So I knew that my center had to be somewhere on this perpendicular bisector. Then I did it again. Drew another chord, did my perpendicular bisectors, drew in that, I did my arcs there. So where those two intersected had to be the center of the circle. Okay? So I said, "Dad, there's your center of the circle." Like, "No, it's not. Dad, it's the center of the circle." So I got my compass out and everything. I mean, I had to sharpen my pencil several times. It's very difficult to do constructions on like fighting. Okay? I go, "Dad, trust me. I got this." He goes, "I don't know." But "Dad, this is my bathroom. I paid for all these supplies. If I'm wrong, I'll pay for a new board. Like, it's okay. Just try it." All right. So he's all nervous. He does it. Bingo. It's perfect. So, "See, Dad, I told you gotta trust me." He goes, "Well, I guess your degree finally paid off." I go, "Dad, like, I have my own job, I have my own house, I've been paying my own bills, like, it's paid off long before then." But that theorem saved us. And I got a bathroom and I got to move home 6 months later. The long 6 months. Okay. So that's why it's my favorite. Thanks for asking. I also want to show you why measuring is so important when doing plumbing. This is the bathroom at Cheddar's. Ladies, gentlemen, hopefully you've never seen this, but ladies, the middle stall, the Cheddar's bathroom. Anybody back me up here? Do you see how awkward this seat is? Look how close this wall is to the toilet versus here. Anybody got me on this one? It's bad. It's bad. Like you sit on the toilet and you're like this. If it's so bad. Another important reason, measuring bathroom safety. All right, so on your notes, I have 5 circles towards the bottom of your page. In the middle, there's 4, and there's 1 towards the bottom. What I'd like to do is give you 5 minutes. I want you to just think through these problems and try them. Now, fair warning, there are going to be some measurements that it's not possible to find. Okay, so I'm going to give you 5 minutes to think, and then we're going to go over it. I'll tell you why you can't find them. Okay? So 5 minutes, try those, and then we'll go over it. All right, so for the first one here, I noticed that my circle angle is 100 degrees, which means this arc is going to be 100 degrees, right? Over here, I know if this angle is 50 degrees, because of my isosceles triangle, this angle must also be 50 degrees. Okay? So that means the central angle here, if I put them together, is 100 degrees, which matches this 100 degrees. Okay, so When they list the 8 right where they did, it's just referring to this short piece. If they wanted it to be intended for the whole chord, they would have placed it right here in the middle. Okay, so it's a little tricky sometimes to read in circles. But if this section is 8, remember it's bisected, so this section is 8, the whole thing is 16. So because we have two central angles that are same, this chord then is also going to be 16. A lot of people want to say that y is 16, but we actually don't know that. Okay, we cannot find y in this situation because we don't know the measure of its central angle. And we don't know the other central, we don't know this other missing central angle to determine if we have a 100-degree angle. Okay, so we are not able to find y in this case. All right, next one. Next one here. I notice I have a radius here and it is bisected this chord. Right, it's bisected the chord, which means that it must also be perpendicular. So W has to be 90 degrees. In this scenario, B is referring to the radius. We cannot find the length of B. Okay, B is not possible. However, that being said, sometimes you'll see circle problems where they'll say, like, this piece right here is 3. If I knew that section right here was 3, I could redraw my radius anywhere, and it would still be V, right? And so I'll have a length of V. If I did that, then keep in mind, I could use Pythagorean theorem to solve for that radius. So you can draw a radius anywhere you want in that same circle. In this case, you couldn't because I just made up the 3 now, right? But keep that in the back of your mind. You can draw a radius anywhere you want it. All right, next one. Next one. So here I notice I have 2 congruent chords, which means I should have 2 congruent arcs. So W has to be 100 degrees. I notice I have a triangle, and because the legs are made with radii, it's isosceles, which means that this other base angle has to be 35. It's still a triangle, so there's 180 degrees. Subtract what we know. We're left with a 110-degree angle there. So if my central angle is 110, then my arc has to be 110. Now, if I have my whole circle is 360, subtract what I know, right? My 310, I'd have 50 degrees left. Is that one okay? Okay, next one. I have a little segment here coming from the center. It's bisecting it, so it means it's also going to be perpendicular. So really what I've created here is a right isosceles triangle. Okay, so these 2 base angles have to be congruent, and they're both going to be 45. All right, last one. Last one. This one's probably a little bit trickier. Okay, so notice here I have a 66-degree arc, and then all the other arcs are associated with congruent chords, right? So all the remaining arcs are going to have to be congruent. So if I take 360, subtract what I know, which is a 66, I'm left with 294. If I divide that 294 equally among all the 6 remaining arcs, it's going to be 49 degrees. Right, 49 degrees for every one of those. Is that idea okay? All right, now, if I know my arc is 49 degrees, then that central angle there has to be 49 degrees. So now, this is a radius, right? Or these 2 are radii, so I have an isosceles triangle. So my base angles have to be congruent. I think we did 65.5. Yeah, 65.5. So both of these base angles are 65.5. Okay, now we can use that triangle and the idea of isosceles triangles if I were to draw in some more triangles. So what I did is I drew in this here. So I drew in those 2 extra triangles with radii. Okay, so I made isosceles triangles. We already know this triangle right here the arc is 49. My central angle has to be 49. I know this part has to be 65 and a half. For my other triangle that I just created, if the arc is 66, the central angle is 66. Right? So 180 subtract 66 and divide by 2, you get 57. So this is 57 and this is 57. Excuse me. So these two angles here make up x. Right? So if I add them together, I have 57 plus 65 and a half. We get 122 and a half for x. How do you feel about those? That was a little trickier, a little more involved. That's kind of the fun part of it too. All right, for homework, you have a worksheet there. I didn't leave you a whole lot of time, so let's do this. Either do all the odds or do all the evens. Okay, you pick. I'll give you all the answers, but you pick either all the odds or all the evens. Okay. Any questions from today at this point? Okay, so you can start on your homework. If you need help, let me know.